Okay, I believe we can start. Hello, everyone. On this conference, third edition, as far as I believe. I'm very happy that I'm here today because I always wanted to be here, but not always everything that we want is possible. But I'm here today, we are here today, and we can talk something about performance. I'm very happy that so many people come to listen about performance. So let's talk about performance in C#. My name is Konrad KOKOSA. A very simple slide about me. I'm a guy related somehow to the performance in .NET in general. I wrote this book, which is about .NET memory management. It is only 1,000 pages because it is automatic, so there is nothing to say about it. It weighs 2 kilograms, by the way, so it's quite heavy, but maybe it will be interesting for you. I also a co-founder of such initiative that is called .NETOS. It is an initiative about performance and internals in .NET. I'm also currently involved in development of a card game. Do you play card games? Someone is playing card games? No one? Few people. If you are interested in card games, I'm developing card games for .NET developers. Very nerdy one. You have memory leaks here and so yeah, and that's all. Also, you can, if you are interested somehow in .NET internals performance, follow me on Twitter simply, and because I'm tweeting about that. Okay, but speaking about all that, the topic of this talk is high performance code design patterns in C#. So what high performance is in fact? Yes, this is maybe even quite strange because is C# something that is made to be high performance? If you would like to write something very high performance, probably we would be using C or C++ or Rust, but I don't think so because I'm a C# developer. I want to write high performance things in C#. And it is possible because Microsoft is doing more and more to make it possible. So it is high-level language, but provides a lot of possibilities how to write very, very fast code. And this is a talk about that. And having said all that, this is not a talk about like application performance monitoring. It is not about architecture or front-end performance. It is not about caching or databases, because databases are being slow, are a place where we optimize things. But this is not the talk about today. This is talk about solely about C# code level performance. If you have this small part of your application that is really should be really fast, and it is written in C# because you are writing code in C# as far as I believe, we want to write it as fast as possible. And then we will have some design patterns because I'm somehow following the whole ecosystem of .NET in terms of performance. I'm seeing more and more patterns that are common, and so I decided to I decided to list them. So simply, let's make some kind of list. Like there was a object-oriented design patterns, so I thought maybe I will provide kind of list of design patterns related to performance in C#, and this is talk about that. So having a design pattern, like have anyone of you read the original object-oriented design patterns book from the Gang of Four? It is kind of Bible related to the design patterns in object-oriented programming. And then there was a design pattern described one by one, and every design pattern obviously was a solution to some common problem that is frequently occurring, because as an industry we have some common problems that they occur frequently in different contexts, but the solution can be common. So it is why design pattern is beneficial, because it contains expert knowledge about the topic, how it can be solved, contains best practices, allows us to avoid the problem of reinventing the wheel, because there are common problems, so why we should reinvent the wheel and try to solve this problem again and again. So it is very beneficial for us as a list of problems, solutions to problems. And in general, they are based on some more basic principles like solid principles, clean code, and loose coupling, high cohesion, a lot of principles that were driving design patterns. The same can be applied to design patterns in performance. There I identify at least 8 principles that can be describing the most fundamental ways why we should design something that or another in case of performance. So there are also principles about the performance, but this talk is only 50 minutes, so I'm not describing principles. At the end of this talk, there is a link with the longer version of this presentation. There, these principles are listed, so you can refer to that at home after the conference. Here, I'm just describing design patterns because we have limited time. So each design pattern obviously has a name because we need a name. We have some problem that this design pattern is trying to solve. We have solution, obviously, how we solve this problem and what are the benefits. Maybe there are some other benefits than only solving the problem. And obviously there is always kind of drawback, so maybe there are some potential problems when we're using such design pattern. And with this structure, every design pattern was described in case of object-oriented programming design patterns. So I tried to also apply this structure to my design patterns. All those patterns that I'm describing here are my own findings, let's say. There is nothing like industry standard and nothing that was proposed. So every name is also by me. Maybe you can suggest better names because naming is hard, so I have some design patterns here named somehow by me. So the very first pattern, because this talk is about patterns, so I'm providing you some patterns. The very first is called by me fragile object. Fragile is not so popular word in English. I also needed to find some good word for that. Fragile means just not willing to spend a lot of money in general. So in our case, we need an object that is not willing to spend a lot of everything, like memory usage, like overhead of kind of memory access. We need some objects that will be fragile in that term. And so this pattern is about, we need to store efficiently some data structure that can take various forms. And the typical, as we will see, the typical case here is a collection, because collection is this data type that needs various forms. Like we have one item, maybe we don't have any items, or we have many items. So there is a kind of variety here. So the solution is we can provide kind of discriminated union that stores that various values. Maybe the code will be speaking the best. So this is an example from ASP.NET Core code. There is a type string values. And this is a type that represents collection, in fact. It can represent 0, 1, or many strings. And obviously, if you are using something like that in your code, you will probably use list, because it's the collection. It can represent 0, 1, or many strings. So we will be using list of strings. Here we have something maybe not so intuitive. We have only struct, because structs are more lightweight in most scenarios. Moreover, it contains only one field, and this one field can represent 0, obviously, because there will be null. It can represent single string, or it can represent many strings. So it is quite strange code for us, simply because why we are doing such magic? It provides a lot of benefits, in fact. Obviously, in terms of memory usage, it is less. In terms of accessing, this is now more complex because, for example, when using indexer, we need to check whether we have zeros, whether we have one string, or maybe there is, in fact, a collection underneath. So maybe the access will be slower, but in terms of creating this struct, in terms of memory storage, it is more frugal. And in fact, a lot of such collections we will meet in various code bases, like Dmitry Ivanov recently tweeted about that fact, even that a lot of code bases is trying to represent somehow a collection that most often contains a small number of elements, because using list is just an overhead here. And he provided some examples because he is working in JetBrains, so he provided very similar real code from their code base from JetBrains, like compact list, which is exactly like that. It can represent one element or many elements. or you can extend it, because let's say that you know that you're in your code, you have a collection, you are using this collection tremendously often, and you know that most often it contains at maximum 2 elements. So you can code a special crafted collection for you, the fragile list, which would most typically contain only those 2 elements. And now the locality of data is much better because we don't have this list, which is in fact a reference to an array, and the array contains references to objects. Now we have these objects, references to objects directly in our list. And all those are structs, because probably we will be using it locally maybe, so it will be, for example, JIT optimized, and it will be not even on the stack, maybe they will be in registers, we will not know, but for sure it will be the possibility that it is faster. Other examples, the WPF code have exactly like that. It has a kind of special list that is baked by 3 types of lists, which represent single item, that represents 3 items. They have also a code for list which contains 6 items. So again, quite strange code that is providing us much better data locality because we are handling this collection in a special way. Obviously, every fast code is ugly. So this code is ugly also because we have this drawback. If we want to have fast code, probably it won't be beautiful. But yeah, this is like work is working. So I provided, so this is a very simple example, list of often 1, that we are using a list which is often 1, so we can write code like that. It is a clone of the code that I was showing you, like string values. It has only 1 field object, it is a struct. Obviously now accessing this is much more complex, but still it is not it is not a magic, yes. So we just need to somehow write accessors that take into consideration what really this object is. But in terms of performance, we gain something, yes. For example, creating now this very small type for empty case, for single item case, it is much faster and consumes much less memory. Because of this more compact way of organizing our data. So this is one of the examples how writing something not obvious provides us a performance benefit. Okay, this is the very first one. So we provided much better data locality. We are using smaller memory. Sometimes accessing the fields of such array might be, such collection might be slower because of all those checks, but not so slower. It's always a kind of compromise, and we need to think whether it is beneficial for us or not. For sure, it is kind of pattern that we can recognize in current .NET code. Fast one, obviously. You won't be modeling domain with the help of such things. The second very tremendously popular pattern is pooling. So in case when you have a lot of objects and you are creating a lot of objects, the cost of creating them is not trivial. We can somehow avoid this cost by pooling objects. So instead of creating every object we need, we can reuse some objects from some pool, pre-allocated pool. And this is also a very, very popular solution to this problem currently called array pool. So most typically the most costly objects in .NET are arrays because they are bigger, so we need to create an array and somehow find some memory for it and so on and so on. So creating arrays is a way of making overhead. And if we are creating a lot of arrays, instead of newing them up every time we need them, we can use this array pool. Have you used array pool? So in your code, few hands raised. So this is a very API as you see. It's there we have a array pool shared instance. We can rent an array from it, operate on this because we get a regular array. In fact, we can consume somehow this array, and when we are done, we need to return it to the pool. So this is a quite easy API, in fact, and provides us this tremendously good benefit of reusing these arrays. So we don't need to create them every time. We are just having some buckets with arrays with given size, and the arrays are reused every time we are using array pool. Very, very nice and quite easy fix if you are using a lot of arrays. So imagine a code that is doing something like that. We have a code that needs some temporary collection. So we have input data, which is represented here as an items field. We need to pre-process these items somehow to a temporary collection and then send this temporary collection to some further API represented here as a process batch method. What is important for us here is that with this very first simple solution, we are just using a regular array, which we are using a newing app every time you need this array as a temporary collection. So benchmarking this provides us some result. It is doing this in that time. It allocates a lot of data, obviously, because we need this array every time. So we are allocating this array. And we can very easily change it to using array pool because the API won't change a lot. Now, instead of newing app, we are just using array pool, renting, using this. And when we are done, we are returning this to the pool. And it provides quite good benefits in terms of performance now. Obviously, it is, maybe not obviously, but it is much faster, almost twice faster, like the original one. And look at the allocated column. Now we are almost not allocating anything. So because we are reusing already allocated arrays. So in terms of memory usage, it is a huge benefit. But we can do better, as we will see. And this pooling is very popular. So we have array pool, we have more abstract memory pool, which represents memory blocks, which is underneath, in fact, also baked by array pool. But the shared instance of memory pools returns as a memory which is disposable. So if you need a disposable interface for your object of your memory, you can use it. You can use memory pool shared instance because it is disposable. So API is more convenient for some scenarios. Obviously, one could ask, okay, this is only for arrays, but what about objects? I need, for example, to reuse strings or my custom class. Currently, there is no public standardized API for pools of individual objects. There was a PR for that, but it is currently closed. We will see what will happen in the future. If you really want to have object pool for individual object, there is object pool class in Roslyn code base. You can simply use the copy-paste method to implement it, for example, in your code. So pooling is tremendously popular, quite easy solution, in fact. Obviously, if you are not writing your own pool, if you are using the already provided pool mechanism, it is easy to apply, but you get a really big benefits. You reused objects, you don't allocate objects, the fragmentation might be smaller because we are reusing the same objects. The memory usage might be much smaller. So very, very popular solution. The pattern number 3 is I'm calling it zero copy because I don't know how to name it better. It is all about avoiding copying memory. So quite often you have some scenarios that you need to operate on subdata, like the tremendously popular case is substring. String has this unfortunate, let's say, substring method, but substring is creating a new string and copying the content of the original string. So in fact, substring produces a lot of memory overhead because you need to create a new string, copy memory to it, and so on and so on. So for us, it would be great to have kind of slicing possibility to provide subsets of data, but without copying memory, to represent somehow smaller regions of original memory. And here, the beloved span of T comes because it is one of the kings of the current .NET high performance code. Span is kind of conceptually easy thing. Implementing it was maybe not so easy, but conceptually it is a very simple kind of data that just points to some memory. So we have these pointers showing what from where we are starting, and in fact, and also length saying how big memory region we are representing. So in fact, the span of t is just saying that we are now representing a memory from here to here. Very simple conceptual thing. But because we are in the underneath of the span using manage pointer can represent a lot of various data types. And this is very powerful things. For example, it can represent, it can point into inside an array or inside a memory region. So thanks to that, we have this slicing possibility. So when we are using span, we have this possibility to represent a lot of. By the way, have you used span so far? Few hands, like I would say 10 maybe. Okay, span can represent our various types. So it can represent an array. It can even creating span, as you see, you can even say that my span is representing this array, the whole array, or a part array which starts at 8 elements and it represents fourth element. Four elements. And this is without any copying. This is only saying that it will point to the inside an array and it will have this length sent to 4, but it is nothing here is not being copied, no memory copy, nothing like that. It can represent stack allocated data that we will be talking about soon. It can represent unmanaged memory, it can represent strings. In fact, every type of memory that you probably could imagine can be represented by span. And all of this has this powerful capability of slicing. So when you have this big memory region, you can slice it. You can say, okay, I have this huge string that comes from HTTP, but now I want to log and I want to slice it into smaller strings, smaller spans, in fact, without memory copying. And this is a huge benefit for parsers, for example, because parsers, if you have ever written or read something about parsers, parsers like to work in descendant way. So they have a huge string and they are interpreting smaller and smaller parts of these incoming strings. So instead of substring, this whole string, you can look at it in spans, smaller and smaller spans. A lot of parsers currently, like JSON's, HTTP Kestrel web hosting infrastructure is using span also to interpret incoming bytes in smaller parts, because when you have a bytes incoming from TCP socket, you need to recognize HTTP headers, HTTP values of the headers. It's all about parsing. So also span will be very popular in dot kind of code. Because span contains manage pointer, there is one caveat here. The manage pointer is a special type of beasts which cannot live on managed heap. So it cannot be boxed. Span of t can't also be boxed. It can only live on stack. And this is quite huge limitations. So the main concerns for us is as async, because async is the other tremendously popular thing in .NET currently. So in other ways, the problem is that span cannot be used in async method. We like async methods, we like span, so there is a problem now, because how to connect them, how to merge those two powerful features. For one of the reasons, and this is one of the reasons why a more general memory of T type was created. Memory of T is slightly slower. It is maybe also slightly less powerful because it cannot represent all types. It can represent arrays, strings. It cannot represent stack data. But it is struct which can be boxed. So in case of async methods, memory of T will be used because it is more general. And from memory of T, you can take a slice also in your method. So this is how you can solve that typical pattern using memory of T in async methods, and from memory of T, you can take spans. And memory of T can be taken from the memory pool, as I was showing previously. So you can use memory of T, which is taken from memory of T shared pool. Other examples, because a lot of changes currently are about avoiding copying. So like refs, a lot of things to C# has been added about refs. You can pass by reference arguments, we can return by reference. There is a lot of things that you can do by reference. There are ref structs. Everything can be shown as a way of doing things in this zero copy approach. And there is a powerful system I/O pipelines new API, which is a producer-consumer collection, which is also all about zero copying, because there both writer and the reader can see data from spans, from the internals buffers, zero copy, just a very fast code to provide a communication between producer and consumer. Also a zero copy approach here. So very powerful thing. If you look at any code which is high performance, for sure you will see Spander and memory of T there, because it is so tremendously popular way of doing zero copy things in .NET currently. Obviously, zero copy is good for us because we are not having this overhead of memory copying. Obviously, there is a drawback because now API is polluted with all these strings, all these strange spans and memory. It is not so clean. We don't have strings. We don't have arrays. We have those strange span now everywhere. So it is kind of very technical thing that now everywhere we see those strange types, but it is a cost. The fourth pattern is called struct of arrays, very popular pattern. When we have a problem, we are designing an algorithm which accesses a lot of data, and the main problem for us is the memory access cost, because there is some memory access cost, and we want to take into consideration this in designing our data structure. So the original approach is we can call array of structs, although there are no structs. We can say array of classes. It doesn't matter for our case. Originally, it is called array of structs. This is how we would write it in the original way. So we have a perfect object-oriented design here. We have class, which is a container, it's just a repository for customers. Customer is perfectly modeled in an object-oriented way. It has private fields which are not accessed. We have this algorithm update scorings, which is very, very popular, very important for us, and we want to make this update scorings algorithm fast. This is modeled in object-oriented way. Yes, so we have some object, and in update scorings we are just accessing these fields somehow because our algorithm looks like that. But okay. This is how we would model it without thinking anything about memory. But from the perspective of memory access, this is a complete disaster because, in fact, the repository contained a list of customers. A list of customers, in fact, is baked by an array of customers, but this is also an array of references to customers. So when processing customer by customers, we are simply jumping all over memory in a random way because we have these customers somewhere in memory. So accessing them one by one is kind of sequential logically, but from the memory perspective, from memory access perspective, it is just random access. We don't have any guarantees here. So baseline benchmark would be like that. Let's see how we can improve it. A little better solution would be to use structs instead of classes, because so the code is almost the same, but we have two benefits here. The customer is now represented by struct, and this is one of the benefits is that now we can use this struct layout sequential. So we are saying that the most important fields for us, for our algorithm, like earnings, scoring, year of bit, and so on, that those fields are at the beginning. So they at least at the beginning when we are accessing memory. And the second, when we are using list and in fact an array of structs, these structs are inlined into the array itself. There are no references to customers. Now the customers are values, the whole customers are inlined into this array underneath. So yeah, this is better for us because we have the less jumping all over memory. Now customers are laid out one after another in the memory, so it is good. The problem is that the whole customer contains a lot of fields and we are only using some of them. So when we are reading this array, customer by customer, in fact, we are reading some fields that are not necessary for us. So it is another overhead because we need only 4 fields in our algorithm, in fact, but the customer may contain dozens of fields and we will be reading somehow all these fields because we need access memory in some blocked way. So this is not optimal solution. This is array of structs original approach. This approach that I'm going to is called struct of arrays, and it is okay, benchmark. It was better, as we see, not twice but significantly faster because we simply changed this customer from class to struct. But the final solution is the ugliest one, obviously, because we get rid we have just violated every good object-oriented good practices. We get rid of customer completely. We don't have customer entity, whether it was class or struct. We have now only arrays of attributes of this customer, the ugliest thing that you could imagine, probably. But from memory access perspective, it is now tremendously better because we have those attributes Y by 1 for each customers. And when our algorithm will be accessing those fields, those attributes, it will be fully consumed because we have this array of, for example, of scoring attributes. And all those scorings will be important for us. So every time we need something, we access memory, we access the whole bunch of data that will be used for us. There is no single byte wasted here for memory access. You agree probably that the code is ugly. But the result is the code that is 10 times faster than the original one, just because of this completely redesigned way of memory access. So for sure it could be beneficial if 10 times faster code is important for you. If you are processing this and you want to be in real time, for example, it will be very, very important. Recalculating scorings of customers when the customers are visiting your site. Maybe it may be important for you. And this is ugly, as we agreed. All around this concept, there is a more general, a little more well-designed concept of so-called entity component system, which is tremendously popular in game design because game engines are using this, because game engines, in fact, are algorithms that need to update a lot of objects, game objects. So this is the problem that they have. And entity component system, if you are interested, you can Google for it. Unity 3D is using entity component system. There are libraries for C# which are also providing this entity component system. All this is around the same concept of a struct of arrays, wrapped with something much, a little less uglier than the original solution that I showed you. So struct of arrays is much better for performance because of the memory access. Obviously the code is uglier, so it provides much worse design, in fact, but as I said, always fast code is uglier, so sorry. Pattern number 5, tremendously popular approach, avoiding the managed heap, because obviously garbage collector.NET is awesome and everything is working very fast, but the fastest way of code, the fastest allocation is the allocation that is not done at all, because then we don't have allocations. So we will trying to provide something that avoids the managed heap. when we, for example, allocate a lot of small objects, temporary objects, it would be nice to not touch the managed heap, because it will introduce overhead for the GC, and then the GC would need to somehow handle these objects, garbage collect them, and so on. So the best solution for us is just not allocate at all and avoid the managed heap. By utilizing various possibilities, like structs. But structs are quite tricky. Obviously, they provide good data locality. We were using structs in our previous examples. They have many benefits, but still they can be boxed. So problematic thing is that at some scenarios still struct can land on the managed heap. The scenarios when it happens are not so obvious, so sometimes we would like to do something more powerful even than using struct. Obviously, still we love structs, and we will see more and more types that have a struct alternative. Like if you are using async and task, now we have a value task. If you are using tuples, now we have value tuples. All those are structs because they provide much better data locality and so on and so on. But still there are more powerful solutions like stackalloc operator or using ref structs or fixed size buffers. Stackalloc operator is a, have you used stackalloc before? Few hardcore developers in the room. Stackalloc operator is something that returns us a block of memory directly from the stack, because it is very fast, because stack is fast. When we are using stackalloc, what we are really doing is just using a little bit bigger stack frame, but this memory will be living on the stack. There is no GC overhead at all. And since the beginning, we could use stackalloc like that as above, but unfortunately it returned pointer, and pointer required unsafe code, so it was kind of problem sometimes. But since the C# 7.0, stackalloc result can be represented also by our beloved span, so now even in safe code we can use stackalloc. There is one big feature or bug, it depends how you call it, is that stackalloc obviously takes some value, how big data we want, and there is no way to be sure that there is such space on the stack. So when using stackalloc, in fact, immediately you are exposed to the problem that you can be hit by stack overflow exception. And stack overflow exception is one of those exceptions that cannot be catched, so simply it kills the whole application for you. So using stackalloc, you always have this risk that if you be trying to provide and create too big data structure, you can kill your application. It's kind of feature. That's okay. There is not even no official threshold what we can perceive as a small enough, safe enough data size. Few hundred is something that we assume few hundred bytes is probably enough, and we won't be killed. Going back to our example, now we are using stackalloc as our temporary data, so no array from the pool, just the data on the stack with some quite risky code here, because we are just allocating as data structs items with the provided items count. We don't know even how big this data structure will be, so probably someday we will be killed by the stack overflow exception, but still, this is only for example purposes, so we are stack allocating the whole temporary data on the stack. And again, it is much faster, because everything happens on the stack here, and as you see, there is no allocation. There are no allocations at all. Our code will be not allocating anything on the managed heap, only using the stack. So quite nice thing. And it is all 33% faster. There is one thing that probably could be better. Because when using stack, the runtime guarantee, current guarantee of the runtime is that the stack will be zeroed because we need the clear data. So all the stack frame needs to be zeroed to be initialized to zeros. So when we are stack allocating the temporary data structure like here, all this will be zeroed. But we don't need it, in fact, because we are just creating this stack. We are just creating this data temporary structure and then filling it with data. We don't read anything from that. So why we need zeroing here? We don't need zeroing of this memory. And it would be nice to have kind of this attribute that says you that, okay, in this particular method, I don't care about zeroing memory of the stack frame. There is currently no such attribute in the standard approach, but still I was able to do that and measure that. So as we see, there is another benefit, the code become even faster. Maybe this difference is not huge, but still for very, very fast code, it would be beneficial for us. So now we are not zeroing this data, temporary data. 10% faster, it is big or not. For me, it is quite nice improvement. And you can do that with the help of FODI. FODI is a code weaver. It manipulates an IL code. So with the help of FODI and the locals init plugin, you can do that. You can just use this locals init attribute in your methods. It is highly dangerous, as you probably know, because from now every local variable won't be zero initialized. So for example, your references won't be null by default, which is quite risky. But there is such approach. For sure, you should really think about if it is safe in your case. And there is even a PR for adding this to the standard C# libraries to have such attributes, not to use FODI. So in very high performance code, maybe we'll be using something like that. And because of this risk of killing our application, which sounds a little bit dangerous, this common pattern you can meet in your in a code that is using stackalloc. You need some temporary data with given size. So if this size is small, you will be stack allocating this. But if it is big, and this obviously the threshold is problematic here, what is small, what is big. But we have this threshold, and if the size is bigger than this threshold, we are not stack allocating data, but we are just renting from the pool. And in one or another way, we are just having a memory represented by span. So now we can operate on this span, do something with it, with the underlying memory. And when we are done, we need only to remember to return this to the pool if it was taken from the pool. So this is also tremendously popular code that you will see currently, using stackalloc or array pool, depending on the data that you need. There is also like fixed size buffers, which is kind of strange because it is inlining the array inside the struct. So in case of the regular struct that contains an array, it is just a reference to an array. So data locality is not so big, not so good, because obviously it's only reference to some array living somewhere else. And in case of fixed size buffers, you can inline these buffers into structs. So this is just a side note that there is something like that possible. And yeah, so stack-based data will be tremendously popular thing in such code. And in fact, looking at the high-performance code, you will see combination of all those patterns somehow merged into the final solution. The last pattern is buffered builder. Which is also about creating a lot of objects, temporary objects, because we are operating on a data which is immutable, but in fact, yeah, it is immutable, so operations on immutable data provide temporary objects. Ultra popular example is string. Everyone knows that string is immutable, so when we are adding strings, in fact, you are creating new string with the content of the previous ones because it is immutable by default. So we cannot modify the original string. We can only create new one with a little bigger or smaller content. And obviously their string builder as a solution comes. Everyone probably at least once heard about string builder as a solution to this problem. So having these two web API methods, it is producing some XML code with very ugly way. In two ways, in fact. The left solution is based on strict concatenation. So as strings are immutable, we see here creation of a lot of temporary strings, because every line, in fact, is just creating a new temporary string that is being replaced immediately by a new string in the next subsequent line. So it produces a lot of strings. The solution would be to use string builder as on the right side. So string builder is better because the result will be exactly the same, the string with the XML. Solution is here good because string builder operates on a buffer inside. So when we are adding something to string builder, in fact, we are adding something to the internal buffer, and only at the end we are calling to string to get the string from this buffer, but no temporary strings are created. And the result, when we are measuring it, are tremendously different, because here is in Polish, unfortunately, I forgot to change that. But in the left part here is a load test, and the orange line is the GC overhead, percent time in GC. There is such performance counter. And as we see in case of string concatenation, during the load test, in average, 60% of the process was in the GC. So in fact, mostly the CPU was doing GC in our case of this load test. In case of the string builder solution, the right part of this load test, obviously there are some pikes, but in general, GC overhead would be at the level of 15, let's say, so much less. And moreover, from the perspective of the client, the throughput is tremendously different also, because in case of string concatenation, such API would be able to process in average 9 requests per second. And by just replacing it with string builder, it would be bumped up to the 150 requests per second. So tremendously different application, in fact. The same result, code is working, but in left case, we are just consuming every CPU cycle, in fact, for GC. And on the right side, we are just doing the business thing. So we will see this kind of buffered builder, as I'm calling this, in various scenarios. Like big integer, for example, is also immutable data structure, which can represent every number, no matter how big it is. And all this plus, minus, division, multiplication is also producing a new big integer. So for the memory perspective, for better memory usage, we can provide some kind of builder for big integers, and there is a proposal for that to expose such builder and have this smaller overhead here. And those methods, add, divide, multiply, will be operating on some internal buffer, and only at the end we will be calling two big integer to get this integer as a result. And we can think about such builders. There will be many different builders. You will see such builders in the fast, let's say, high-performance C# code. Typically, it's not probably time here to describe all this, but you will typically see this, that they are used like that, because we have this combination of possibilities now. We have a kind of builder that needs an internal buffer, and this internal buffer can be stack allocated to be fast. It can be represented by span, and we can provide this builder with this initial buffer, which is stack allocated. So it will be very, very popular way of doing that. We will have such buffered builders that will be buffered by stack allocated data. Obviously, we can also extend it here with using of array pool if the buffer would be, we required a bigger initial buffer, but still it will be a very popular way of solving such, creating and designing such buffers. Yes, and it will provide a lot less memory usage. So a lot smaller GC pressure, because everything here will be designed to operate on the stack. Obviously, this was only six patterns. I could provide 2 talks at least, more, about different patterns that you can recognize. Those are chosen by me because I believe they are most popular. There are another pattern candidates. And I'm creating a GitHub repository which will contain all this, so follow me on Twitter to see that. Like, for example, currently hardware engines are very popular to vectorize operations of data. This is also incoming very popular thing. So, having all that, this was a 50 minutes version of the talk. Under this link, there is a 2 hours version of this talk, which also contains a little more details and those principles that I omitted. I invite you to look at it as a kind of notes from this talk. And that's all. The timer is red, so I probably should stop talking now. Thank you. The question is if we have a time for questions. We have time for questions. So do you have any questions related to all this? Okay.
Hello,
Very simple
question
questions.
from
Show the link
me.
again.
Thank you for presentation. Some maybe generic question. So all this, let's say, optimization or writing high-performance code, were there any cases or are there any cases when you are starting writing it exactly from scratch? Because my understanding is that we have some code and we start to do all these things only when we have some issues or we have problems. So are there any cases when we are starting to doing all these, let's say, patterns, for example, from the scratch?
Most typically, I would say that for sure measure first is the mantra. So you have some application, you have to measure it and you know where are your bottlenecks. Maybe they are known, so it's okay. If you have some bottlenecks, there is a place to apply them. Unless you are writing something that by design should be fast and you know that you will need to fine-tune to the boundaries. Like, for example, you are writing a parser or something, or event engine, or something which is by design low level enough that you for sure know that you will in fact end in optimizing it like that. I would probably start doing that from scratch using all these patterns because I know that in the end I will be using them. So, but only for really specific things, like probably most of us is not doing like writing own parsers of languages or writing database engines or kind of like that. So for that scenarios, I will start doing it in that way. From others, I would try to delay it as long as possible because we will just pollute our code with bad, ugly code without maybe big benefits. So,
thank you.
There was a question.
Hello, thank you for the presentation. There's actually one practical question for why. Actually, we are implementing a parser, and one thing that we were missing is the lack of switch over span of characters. Actually, I want to like advocate for this being added to CoreFX or whatever. Maybe your compiler, because you know you don't want to pollute the code with these low-level designs and the consumers of the parsers, let's say. Could you elaborate on that? Whether this might be planned in future C# release or?
I don't know if unfortunately whether it's something like that is planned. Currently, we are just simply have this possibility to write something in a good C# and in this ugly version of with the help of all that. So I'm not sure. For sure, a lot of things is going under the Rosin compiler or JIT optimizations are done in the way that a lot of things are going to be added out of the box. So me as a person involved in performance kind of consultancy, it makes my job less and less important because a lot of things will be working fast just because they are designed like that. But we will see. I don't have any definite answer here, unfortunately.
Thank you.
Any more questions?
There is one here
I don't see where.
at the end.
Oh, okay.
So my question is, there are obviously some patterns which we could apply while trying to optimize our code, but the question is regarding the stack allocation things. Why would I want to play with stack alloc instead of wait for my compiler or just-in-time compiler to finish escape analysis or other optimizations, which it could finally apply to greater benefit than just my changing code and making it ugly, as you said.
Mm-hmm. I mean, it is always like if you really want to have full control over it or just want to rely on something that will be automatic. For sure, escape analysis as a thing that is added but currently not enabled by default. Escape analysis is a new powerful feature in .NET which will just notice that your class, whether it is a class, but still it could be stack allocated because you are using it locally, so it is a very powerful thing. But it will be for classes. There will be limitations in what scenarios, in fact, escape analysis will work. So and for sure it will be not working for bigger data because then JIT will be a little bit afraid of doing it on the stack. So if you really want to force it to be on the stack because you know better than JIT and probably sometimes we know better than the automatic analysis, then I will be just using stackalloc because for bigger data structures, for example, I believe we will need to force using stack still, even if the escape analysis will be there. For sure, for some, so simply put, for me, it will be just a way of doing this and forcing it manually because I really want to have it, not to rely on the current escape analysis algorithm. But as you good point is that for sure, and as I said previously, a lot of things will be working out of the box fast, and a lot of these design patterns like using structs instead of classes will be less important because of escape analysis.
So a follow-up question to this, as you showed on your slide, allocating anything on the stack is risky because of Stack Overflow exception. Catching it in C# is non-trivial, but definitely something we may want to avoid doing in production code. So again, why would I want to force the code to allocate something on a stack, especially that it may crash my application and stop me from doing anything useful and not rely on the escape analysis then?
It's just a compromise between the performance and a little bit of risk. I mean, even Microsoft in their base libraries is using stackalloc quite popularly. Small stack allocated data, like for less than 100 bytes, is no risk probably at all. And they are just approving this in their own code because, okay, it is really, really hard to assume that we have so less stack that we won't be able to allocate 100 bytes. So for such small bytes buffers, for example, the benefit is obviously there's much better performance, no GC overhead, and it is so big benefit for us that we allow this a little risk of Stack Overflow exception. It is just the compromise that you have to decide whether this performance benefit is good enough for you to have this risk, simply. There is no better answer probably. Okay, I believe it's time to end because there is a break and we need to rest before the next call. So thank you again. See you around.